In section 3-1, you're going to be using graphs and tables to solve linear systems. So I want you to be able to solve systems of equations by using graphs and tables, and classify systems of equations and determine the number of solutions. So let's first talk about what a system of equations is. That's when you have a set of two or more equations containing two or more variables. A linear system is a system of equations containing only linear equations. Now, a solution to a system of equations is the set of points where the lines intersect. A point is a solution to a system of equations if the x and y values of the point satisfy both equations. So let's look at an example. We have a system of equations here, and we want to see if 2, 4 is a solution. So basically you just have to plug in 2 for x here and here, and 4 for y here and here, and see if those equations, the first one turns to -6 and the second one is equal to -8. So when you set these up, we have the first and second equations here. So I'm substituting in x equal 2, y equals 4 in both of these equations. So 2 for x here, 4 for y here, and I can see that that comes out to 6 equals 6, so that one is true. And over here I have the second equation. I'm substituting 2 in for x and 4 in for y, and when I simplify that, I can see that that is a true statement. So this is a solution to that system. It has to work in both of them. If it doesn't work in the first one, then you don't have to try the second one. All right, solving linear systems by using graphs and tables. Here is a system, and we want to graph the system to find the solutions. So here, this one looks the easiest thing would be to use the x and the y intercepts. So that's what I did for that one. It's going to cross the x-axis at 4 and also the y-axis at 4. So I have those, here's 4 and 4. So we're going to draw a line, again, go all the way across your graph. Don't want those short stubby lines. And then the second one I just put in slope-intercept form. So I solved that by solving for y. And it's crossing at -2, having a slope of 1. So I'm going to go up 1 over 2. And a lot of times if you keep going up 1 over 2 with the slope, you're going to end up intersecting the line, the second line. So again, all the way across, and we can see that that's our solution. So the solution is at 4, 0, because that works in both equations. The same is true if you're graphing using tables. You just plot your points and find the points of intersection after you connect the points with lines. All right, last thing that we need to talk about is classifying linear systems. And when you're graphing two lines, one of three things can happen. So let's look at that. You could have two lines intersecting at one point. You could have the same line actually being one line on top of the other line. And here the lines could be parallel. So when you have exactly the same line, the lines are intersecting at every single point. That's why it's an infinite number of solutions. The lines are parallel, they're never going to intersect, so that's why that one is no solution. And here's how you classify. If there is a solution, it's called consistent. And because there are two cases where it's consistent, you have to clarify if it's independent or dependent. Now, independent, think of independent people. They like to work alone, so there's only one here, one solution. Dependent, they're depending on each other. One is right on top of the other. So this is consistent independent, one solution. Consistent dependent, infinitely many solutions. And then inconsistent means there is no solution. And there's only one case there, so you don't need a second word there to clarify. All right, to classify a system of equations, you want to put all lines in slope-intercept form and then just look at the slope and the y-intercept. There are two cases, like I mentioned before, where the system can be classified consistent. So for this reason, when you use the word consistent, you must choose between independent, which means one, it's a loner, there's only one point of intersection, and dependent. Now dependent, they depend on each other, so the lines are right on top of each other. So that means, again, they're going to intersect at every single point. Okay, so there are 3 cases here, and we're going to talk about each one. If you have different slopes, that means that the lines will eventually intersect. So the system is consistent and independent. If you have the same slope and the same y-intercept, that means the lines are the same. So the system is consistent and dependent, and there are an infinite number of solutions. If you have the same slope but different y-intercepts, so the slope is the same but they're crossing the y-axis at different places, that means that the lines are parallel. So the system is inconsistent. So we're going to classify one system, and then I'll give you some examples to try on your own. The first thing that we want to do is we need to put this in slope-intercept form. So when we put them in slope-intercept form, the first one here, I just need to subtract x from both sides, and I have y equals negative x plus 4. The second one, I'm going to move the 4 to the other side. So now I have 2y equals x minus 4. I'm dividing by 2, and I end up with y equals 1/2 x minus 2. Okay, now I'm looking at the slopes. That's the first thing I'm going to look at. This has a slope of -1. That has a slope of 2. Or sorry, it has a slope of 1/2. So that means the slopes are different. They're eventually going to intersect. So it's going to look like this system right here. Different slopes are always going to intersect at one point. So that system is going to be classified as consistent independent, which means it has one solution. And we really don't even need to look at the y-intercept for that particular case, because we know, again, if the slopes are different, then eventually the 2 lines will intersect. Okay, you have a few questions to try on your own on the next page.